So hello again. Tonight we're going to talk about intragalactic Lagrangian points or Lagrange points. Interesting extrapolations at the end. So you probably are aware of the Sun-Earth system of L points, L1 through L5. You can see there in the picture the sun sits in the center and the Earth is out there on the right. The rest of the entire solar system is not part of the picture at this point. We're just concentrating on Sun-Earth system. And the interesting thing is these are gravity wells. So they're not actually places where you can orbit. They're places where there's not a lot of gravity pulling you towards the sun or towards the Earth. They're kind of like balance points between the two. And you have a couple of them. You have L1 and L2, which are on kind of the sun side and the away from sun side. The moon actually is between L1 is between Earth and L2, orbiting the Earth. L2 is about 1.5 million kilometers out, about 1 million miles out from the Earth, much farther than the moon. But then you see L4 and L5, and L1 and L3. Think about it for a moment. If you wanted to launch a probe that didn't have that much fuel, and you wanted to put it in a good spot for observing the sun, and the sun does slowly rotate, so you get to see all the sun. You won't get to see the North Pole and the South Pole of the sun. For those, you have to fly over the sun. But if you just want to look at the sun, park it at L1 and look there. So at L1, we have SOHO, ACE, WIND, and DISCOVER. Those are Earth artificial space probes that are sitting about L1. At L2, the goal there is I want to stare away from the moon, Earth, sun system where all the bright stuff is. I want to stare out into deep space, but I want it to sweep around with the Earth as it goes around the sun for a free ride orbit. So we put things at L2. So at L2, you have your deep space observing things. You have JWST, Gaia, Euclid, and Spectre RG, which happens to be a deep space radio telescope that Russia put up there. Now they don't run into each other because there's 1 million miles of space around L2, and they actually fly what is known as a virtual orbit. So there's nothing actually sitting at L2. At any of these L points, there's nothing right at the L point. It's just a kind of a, if you were doing a roller coaster ride, this would be the bottom of the two peaks. So you dip into it, and if you're going slow enough, you kind of move back and forth at the bottom. And that's what these gravity wells offer you, is a low fuel position where you can hang out in kind of an equalized gravity with things out at L2. Now, L4 and L5 we found were great for looking at the sun from two different points of view, kind of like stereo audio. So we had two probes. We sent one to L5 and one to L4, and they were called Stereo A and Stereo B. I don't know why they didn't call them like Stereo L4 and Stereo L5, because I keep forgetting which one we still have. But as they ran out of fuel, they kind of got nudged by the solar wind, and they wound up going around the backside of the sun through L3 and then coming back. So it started out as L4, went through L3, showed up at L5. But when Stereo B wanted to do the same thing, it had a thruster misfire, and it sent the craft into kind of like a high-speed spin, and we lost communication with it. It could still be out there, spinning around, having nobody to talk to. Can't ever point it home. Stereo A is still around. I don't know whether it's at L4 or L5, but it's drifted into one of those two. And Stereo B, we've lost contact with. But the Spitzer Space Telescope, the infrared precursor to JWST, the Spitzer is at L5. Hayabusa, the Japanese probe, is at Hayabusa 2, is at L5. L5 also has an asteroid 2010 SO. Not only are these convenient gravity wells for us to put space probes there, it's also convenient gravity wells should something that is rogue in our solar system be going by and happen to not have enough oomph to get out beyond one of these gravity wells. It gets stuck in the gravity wells. And since L4 and L5 are so large and the center is a deep roller coaster stable, if you drift through L4, L5, you're likely to stay there. The weird thing is you can be an asteroid at L4 and the solar wind can push you around and you'll drift in a low energy orbit until you hit L5 and you'll stabilize again. And then the solar wind can push you again past the Earth back to L4. So there are debris items that are what they call Trojans, which is what they call these things that wind up in these gravity wells, Trojan asteroids, and the Earth actually has Trojans. There are smaller chunks of debris that wind up in these gravity wells in orbit with the Earth around the sun. And yet that rule about what's a dwarf planet hasn't cleared out its path around the sun. Yeah, there are very few things that have actually fully cleared out their path around the sun, not even Earth. So Earth is a dwarf planet? No, of course not. Don't be absurd. But I also extrapolated and said, well, if the sun and Earth have one of these systems of gravity wells, then why not other things? And turns out, yeah, the first known Venusian Trojan, asteroid 2013 ND, just found back in 2013, is that L4 of the Sun-Venus Lagrangian system. So there's more than just that. Well, that's kind of like the planet-sized stuff. What about smaller stuff? It turns out, even within the Sun-Earth system, there is an Earth-Moon system, where you have 5L points associated with the Earth-Moon system, because the moon is smaller in gravity than the Earth and happens to be at just the right distance to create the 5 points. So at L2, we've put probes that like to look at the moon. Okay, so L2 is the backside of the moon. So if a probe that China lands on the backside of the moon wants to communicate with the Earth, given that the moon L2 is farther out, not quite the Earth L2, but on its way to getting there, you can put like the Chang 5 T1 at Earth Moon L2, and it can see around the moon and communicate back with the Earth. So you might say, how did that probe that they landed on the far side of the moon communicate with Earth? By the probe they put out at the Earth Moon L2. Oh, it could see a wider field of view because it's at L2. Wouldn't that work for other probes? Yeah, remember me talking about L4 and L5 are good stereo spots for looking at the heavier mass object in the center? At one time I talked about the NASA Deep Space Network and how we have these giant radio telescope arrays on the Earth for communicating out into deep space where we put probes. Well, the ones that are used to link those ground stations to one another, those are relay satellites. So we put in Earth orbit relay satellites that can relay from like Australia to California by being over the Pacific Ocean at geostationary orbit. And these are called TDRS, telemetry data reconnaissance, or telemetry data relay satellites. So the Deep Space Network talks between stations using TDRS satellites, and NASA's proposing that in the future, when we have lots of stuff going on the moon, we need a way of talking to things that might be towards the backside of the moon, towards the far side of the moon. So if we were to put TDRS-like satellites at Earth, Moon, L4 and L5, they could act as relay satellites for stuff we put on the far side of the moon. And they would always have a view of half of the moon and half of the Earth. And if you put one at L4 and one at L5, you now got covered like 2/3 of the Earth. And if you count Earth to moon, the whole of the moon covered. So you now have communications relay that can see to the far side of the moon. Another thing is, since the Earth-Moon system is closer to us, we can actually see not only larger rocks, but we can see like dust clouds, smaller particle stuff using radar from Earth and then using optical infrared telescopes to look at those spots, L4 and L5. And what we find is, hey, there's a guy has his name on it there, Kordylewski clouds. These are clouds of fine dust particles in our solar system that get trapped in the Earth Moon L4 and L5 because they don't have enough energy to carry them out of there, and they fall into the L4, L5 gravity well and clouds of debris there. Where's all the debris coming from? You know those things called comets that zoom around the solar system and they have tails? The tails have debris? Well, if that debris passes through the L4, L5 of the Earth-Moon system, that adds to the debris cloud. So micrometeoroid dust all over the place. And we have vacuum cleaners picking it up. What about the bigger stuff? Yep, turns out that Jupiter has its own L system. There are two groups of asteroids that are, because Jupiter has a lot of gravity, that are trapped in Jupiter's L4 and L5. They're the Trojans. We first found them at L5, and we called them the Trojans. And then through further observations, we found out, oh, look, there's another camp of Trojans at L4. So how do we label one versus the other? We didn't call them Jupiter, Trojan, L4, and L5. We called them the Trojan camp and the Greek camp because we're into mythology. Now, NASA has a space probe on its way, doing a lot of slingshots around various planets to get it out to Jupiter, called Lucy. Lucy is going to be doing a slingshot to the point where it goes around Jupiter and then goes back into L4. And when it comes into L4, it's going to observe a number of things in L4. And then it's going to use its ion propulsion to get itself out of L4, and it will drift around until it winds up in L5, and then it will slow itself down and stay in L5 for a while. So it's going to do kind of a local survey of Sun, Jupiter, L4, and then Sun, Jupiter, L5. So these are very handy things. Well, what about other L systems in our solar system? Turns out that Saturn, Uranus, and Neptune each have their own sun and planet L systems, typically containing lots of asteroids because we haven't put a lot of space probes out that far. But it turns out that since some of the moons of the larger planets are actually fairly large, they can have a planet-moon L system, just like we have an Earth's moon L system. The moons Tethys and Dione in Saturn's system do have Saturn and Moon Tethys asteroid L system and Saturn and Dione asteroid L systems. Saturn actually have multiple moon L systems. So these L systems are quite common. The basic requirements of establishing a Lagrangian system is you need two bodies, one of them smaller than the other, and by a noticeable amount. They can't be kind of about the same size. One's got to be noticeably smaller than the other. And the smaller body has to orbit the larger body at a certain distance relative to its size and mass. So you got to be in the right spot with the right size body orbiting at the right rate in order to create these gravity well stability spots. And so depending upon the big thing and the small thing and how far away it is and how fast it's orbiting, you can have L spots. Even the Sun and Neptune have an L system. So there's no real limit as to how big or how small you can have, from moons to Earth-sized planets to Jupiter and Saturn-sized planets, and even moons of the large planets. Pretty much a two-body system can have a stability point. So what about a very, very large two-body system? What about the Milky Way galaxy center and our solar system with the sun as the smaller gravity item orbiting the larger gravitational field? So the sun orbits the Milky Way every 225 million years. The distance is about 26,000 light years. Now I've got it on average because it's elliptical. So it's an average. It's less sometimes, more other times. But that's a two-body system, and our sun and solar system is the smaller body. So yeah, there's probably a Lagrangian system for the sun orbiting the supermassive black hole, or the SMBH. That's the center of our galaxy. It does involve some calculus, so I haven't done the math yet, but I'm going to guess that the L points for the sun SMBH system should be towards the outskirts of our solar system, probably beyond the Kuiper belt, maybe into or towards the outer edge of the Oort cloud. But if it got farther away from the sun Earth than about 4 light years, it wouldn't be good because it would fall into the stellar orbit for Proxima Centauri. It would go orbit a different star. So you want something that's going to be, about 30 AUs, 30 times the distance from the Earth to the sun, out to about 2 light years. That large area there, you could have an L1, L2, L3, L4, L5. If some of the astronomics, navigational folks at NASA decided to plug the numbers into the supercomputer and come up with what might be the L1 or L2 galaxy sun L points, what might be there? Well, obviously there's going to be debris there, asteroids, maybe rogue planets, things flying through that get trapped. If we're looking for things at L2, that would be pretty easy because we have the brightness of the core of the galaxy behind us, and it's contributing lots of light to us looking out away at things. But what if there was objects we wanted to look at galaxy sun L1? Now that would be behind us towards the center of the galaxy. That would be very difficult for us to look at. Now we have telescopes that have looked at the center of the galaxy, at the black hole in the center. But they were very large radio telescope arrays. And that's how they got, over a 20-year period of time, the looping of stars in the core of our galaxy around the supermassive black hole, so they could see from the orbital properties where the black hole is. But they need to look even wider than that if they're going to catch something at the SMBH sun L1 position, because that's a very wide number of light years. It wouldn't necessarily be just at the center. If you've ever noticed that we look for comets and asteroids, and we can see a certain number of them as they cross in front of us, but there are others that, hey, one just went by. How come we didn't spot it? Because it's coming in out of the sun. We would have to be observing at the sun in order to see that coming towards us. Well, if something were stationed at the galaxy sun L1, we would have to be looking towards the dense, bright center of the galaxy in order to see it. And if it's just sitting there at L1 and it's small, it'd be very unlikely for us to see it. But we have two things that might be good candidates for taking a look. The James Webb Space Telescope, it's pointing out away from the sun and the moon and the Earth brightness. So when it swings around, it may get to the point where it can, orient itself and look towards a scan along the line of the galactic disk for anything that might be nearby. We're not looking for things that are, 20 light years away or further. We're looking for things that might only be a few light years, a small single-digit number of light years away at L1. There is another probe even farther out that still has working cameras, and that's New Horizons. New Horizons is out in the Kuiper belt beyond Pluto, and it still has working cameras. Maybe they can, it'll have to stop communicating from Earth because it doesn't have a flexible antenna. Stop communicating with Earth, point out, scan around the accretion disk of the galaxy, looking for anything that's nearby, and then rotate back around and communicate the results back to Earth. So it's out at about 58 AU. It would be a good example. The Voyagers would be nice because they're out even farther. They're beyond the sun's influence edge of the solar system, but none of their cameras still work. In order to conserve power, they turned their cameras off decades ago. If we wanted to look at the galaxy sun L1, it'd be tough. So if you wanted to park something somewhere, that'd be the place to park it. As I say, it would be a good solar system observational outpost. So if you're familiar with the zoo hypothesis and the Fermi paradox is one of those things that says, I don't see no aliens. Shouldn't we have seen them by now? And the zoo hypothesis says, they know about us. We don't know about them. They like keeping it that way because we're dangerous wild animals compared to how many millions of years they might be more advanced than us. We're the tribe in the backwater part of the galaxy that they're keeping their distance from us so as to not pollute our way of life, and we don't harm them with our dangerous militaristic attitudes. So that's the zoo hypothesis. But if you are from somewhere out there, if you're from out of town, so to speak, and you do have the technology to get you to the galaxy sun L1 to observe the Earth, would be pretty easy for your technology. Just as we plan to put a TDRS satellite at Earth Moon L4, they could put a communications outpost at galaxy sun L1, and we would be unlikely to see it staring off towards the center of the galaxy, and they could monitor our solar system, not just Earth, but anything going on in our solar system. How big an outpost could they put there? Remember, it has to do with the gravity of the smaller to larger object. And therefore, if the sun is the smaller object compared to the center of the galaxy, then you could put something Jupiter-sized there and it would be stable. You could put a planet-sized outpost there, or you could take one of these rogue planets and park it there, and we would not be able to easily detect it. Is there something there? I have no clue. Is there a possibility there's something there? There's a possibility. But as they said when they detonated the first atomic bomb, hey, there was a non-zero, though low, probability they were going to ignite the atmosphere and destroy the Earth. There's a low probability. Same thing. Low probability, but doesn't mean zero. So in conclusion, these L points exist for any two-body large small system. And there are far more than the Sun-Earth system. Sun-Jupiter has them. That's where we get the Trojan asteroids. And why not the core of the Milky Way and the Sun? Basically our solar system being the smaller body. Why don't we take a look and see if there are things at the intragalactic L1 and L2? We could use JWST and New Horizons. It's my understanding that both of them are looking for their next round of new observation missions. So yeah, somebody should propose it. I can't because I don't have a PhD. I don't work in a science community background. I would have to go find somebody who I could piggyback on, but that would be interesting. Maybe somebody will watch this video and they have the ability to do that. But objects at galaxy sun L1 would be challenging to spot because we'd be looking back towards the dense, bright center of the galaxy where we couldn't see very easily. Wouldn't that be convenient? Okay. And as usual, links. So was that an unusual and or fascinating topic? You're all on mute.
Fascinating, because I understood most of it.
I liked it very much.
No. It's another one of those analogies.
I liked it, but I did have a question.
Oh, well, go ahead.
Okay, now, I don't know why they do this in science, but all these L's are specific to the planet that you're talking about. Like Jupiter has its own L system,
Yes.
right?
Yes.
Now, why couldn't they have caught? I mean, you have to say, in your report, if you were talking about L and you're talking about Earth, for some reason you're talking about both, every time you mention the L level, you'd have to say Saturn L level something or other,
Yes.
or would you say SL or
No.
EL, or you'd have to say Earth level
Yes.
L
Now,
or whatever. Oh my gosh, why couldn't they thought of the different? But is it because all the L systems work the same?
the positions are all different, but the fact that there are gravity wells and there's 5 of them, the concept is the same for all two-body systems where a smaller body is in orbit around a larger body.
And so they know, or the theory is that all of them have this 5 level
Oh,
system.
it's not theory. We've actually, NASA's actually calculated where the 5L positions are for a number of objects in our solar system, and we find stuff there. The inner ones are the ones associated with the Earth and the Moon. Yeah, we've knowingly put probes there because it's a convenient place to park something without expending a lot of fuel. But as you get out into the outer part of the solar system, there's nothing there but junk, space junk, not our space junk, asteroids, rocks and dust and stuff. Now, why they don't call each one of them a different name? Think about it this way. We have this thing called the periodic table of elements, and every one of those atoms has protons, neutrons, and electrons, except for hydrogen, no neutrons. Each one of them has these 3 particles. When we go to describe an element and we want to describe the protons or the neutrons of that element, because it's an isotope and it has, +1 or -1 neutrons. So we want to describe, a baseline or a radioactive isotope of gold, let's say. We don't give it a unique name. We take the number and we say it's got this many neutrons or that many neutrons. We don't say gold neutrons. We don't come up with a new word for gold neutrons because it's the same for all the elements as far as the concepts of protons, neutrons, and electrons. In a 2-body system, the Lagrangian points are the L for Lagrangian. The 5 are the same 5. So you have to the back of the smaller body, to the front of the smaller body, to the left side and right side of the larger body, to the back side of the larger body. There's your 5. Those 5 are the same as gravity well points. They may be in different places based upon the sizes and distances of things, but there's going to be a well at those calculatable points. And NASA has software in their supercomputers that if you can tell me how much the big mass is and how much the little mass is and what the orbital distance and duration are, it can tell you where the L points are. So that's why we, if it's the Sun-Earth L system, we leave off the Sun-Earth part and just say L2. But that leads people to believe there's only one L2. No, for every small to large, small orbiting large body system, there is an L2. So we identify it as, okay, what's the big body? What's the little body? L2. So for Sun-Earth L2, we just call it L2. But for Sun-Jupiter L2, and to not confuse it with the other L2, we have to say Sun-Jupiter L2 or Jupiter L2. But then you throw in the moons, and now you've got to say Saturn has a couple of larger moons that has their own L system that has debris in it, asteroids. So now you've got to say the Tethys Lagrangian L2 or Tethys L2. And then somebody will say, well, wait, what's Tethys? Well, Tethys is the moon of Saturn. Oh, well, why didn't you just say Tethys L2? Because that's different. That's the Sun-Saturn L2. This would be the Saturn-Tethys L2. So there's lots of them, but conceptually they're all the same. There are these gravity wells, these gravity stability points, and there's 5 of them. So that's why they're all called L1 through L5, even though the bodies involved are completely different. Same concept. I know it's a lot of gobbledygook. Did that cover it?
Yes, thank you.
Okay. Any other comments or questions? Had anybody ever heard about things other than the default L points, like L points around other things in our solar system?
No.
Never, never.
Okay.
No.
Do you now believe they exist because Trojans exist? And they are in
Well, yeah, yeah.
L4,
Since you bring it up, I mean, if you believe in gravity, you know, or whether you believe in gravity or not, there's gravity, and so between any 2 points, you have a certain number of stable points that you just need to, you know, put things in a little figure eight, and they'll stay in the same relative position.
Yes, as Neil deGrasse Tyson once said, gravity is the law whether you believe in it or not.
Yeah. Yeah, that would be one of the good things he says. Yeah, yeah, you can. If you don't believe in it, though, you can test it at a window.
Yes. And the other thing is, gravity is one of the strongest large-scale systems in known physics, and yet it's easily defeatable as you lift your hand. So the Earth may be massive, but I can defeat its gravity just by lifting my hand.
Jesus.
So I wonder if there's any amateur astronomers that have ever attempted to conduct I mean, they like to do Messier marathons. Have they ever tried scanning for things in the disk of the solar system out towards the disk of the galaxy to see if there's anything out there that isn't moving? So much like as JWST in orbit with the Earth around the sun changes, if it's looking straight out from where JWST is, it will see different things at different times of the year because it's going around. But it has an orbit of 1 year, which is rather quick. Whereas the sun's orbit around the galaxy is 200 plus million years. So we don't get to see the background sky changing all that often. And our view of the inner part of the galaxy also doesn't change all that often. But if we look at one point in the year and another point at the opposite point of the year, 180 days apart, there may be enough parallax that we can see the farther objects in the galaxy shifting due to parallax, but that anything at galaxy sun L1 wouldn't be shifting because it would be tracking with us with the sun in orbit around the center of the galaxy. So that would be a way to spot something. One of these is not like the other, as the saying goes. All the background stars, if you look at 180 degrees offset for parallax, you could see the stars slightly shift. But there would be something, if it's at L1, that wouldn't shift because it's going with us. So there's a way to observe it. Now, what if we had another planet in our solar system that got ejected from the solar system by a little bit of oomph when Jupiter and Saturn were do-si-doing? What if it got ejected out just far enough that it fell into the intragalactic L1? It would stay there. So if you're looking for a ninth planet, Mr. Brown, I know you're looking over a very big area. You've narrowed it down to a couple of big areas, but check out the galactic sun L1. Just a few light years. Okay, any other comments or questions before I stop recording? Hearing nothing.